So, good morning, good afternoon, ladies and gentlemen, and thank you for attending our webinar on landfill gas technology. I'm Robert Eden, and I'm actually in Bangkok at the moment, where the lockdown is in the process of ending. So we'll be back in the office next week. This webinar is going to last about 35 minutes. After which we're going to have a question and answer session. We have the rest of the team here to answer any questions that you might have on landfill gas. So I'll pass over to Mark Molden, our Technical Director.
Hello, yes, I'm Mark Molden, Technical Director of Organics. I'm based in the UK, in Coventry at the moment. I've been in the industry for just about all my working life. Started on landfills and still doing them now, so hopefully I can assist with any questions related to landfilling activity.
Hi, my name's Keith Richardson. I'm responsible for commercial, most other things, commercial issues within the group. Happy to discuss any aspects of commercial or financial. I'm in the UK at the moment, very wet UK. Spent a lot of my early career in Malaysia. During the 1990s, so very familiar with some of the issues that you're having. I'll pass on to Chris.
Good morning, everybody, and good morning from a timidly civilian Spain, timidly coming out of lockdown. My name is Chris Eden. I'm the Business Development Manager for Organics. I've been working in the industry for over 30 years now. Principally in power generation using landfill gas as the principal source of fuel. If there's any questions related to that, I am very happy to help. And I'll pass over to Brian.
Yes, okay. My name is Brian Johnson, and I work in business development for the Asia Pacific region. And happy to be here today and answer any questions on.
Okay, hello, my name is Jacob. Good afternoon to everyone. I've been working with organics for almost 20 years in this line of landfill gas and others. For the Indonesian audience, untuk audience Indonesia, jika Anda memiliki pertanyaan yang ingin Anda sayangkan dalam bahasa Indonesia, silakan bertanya atau mengetik dalam chat ini, saya akan menjawab. Terima kasih. Thank you.
Okay, that's it. Thank you very much. So we'll just go straight into the presentation of the webinar. So if you could switch off your cameras and your microphones. Avoiding pitfalls and minimising risks with landfill gas projects is a big subject to tackle in 30 minutes, so we're going to need to take some shortcuts. We will cover what we believe are the main items to be aware of to ensure success. Of course, no matter how good the rulebook, there is always the unexpected to address. How to manage crises when they happen is not part of this topic, but more of a life science. Our aim here is to avoid such situations. The first section will address the technical structure of landfill gas projects. Keith and Brian will run through some more fundamental must-dos, and Chris will cover some case studies. We have been working in the landfill gas business for some 35 years now. From the start of the business, when it was still a twinkle in the eye of many a budding landfill gas engineer. During this time, we have witnessed spectacular failures and spectacular successes. It would be good to think the successes have outnumbered the failures, but one thing is for sure. Although many people see landfill gas technology as easy, the number of commercial corpses scattered around the landfill gas time track suggests that this is not actually the case. There will, in fact, be many key messages in this presentation. However, over it all, the one thing we can say with confidence is that landfill gas can be a valuable and viable resource. Whilst landfill gas is not exactly easy, attention to the major pitfalls that are now well known can ensure both bankability and a successful project. The Organics Group started out in 1987 when there were still questions about what exactly landfill gas was. An early debate with one customer was illuminating on pipe sizing. Should we use half-inch pipe or 3/4-inch pipe for a landfill gas collection system? That was the question. Emotions ran high as the cost difference was significant in percentage terms. Eventually, this project evolved to using 10-inch pipes after many years of ever-increasing yields. This highlights how little was known about gas production. From this early caution, we have seen expectations grow exponentially, to the point where landfill gas sites are sometimes seen as gold mines. The truth usually lies somewhere in the middle, although it is fair to say that some projects have been akin to gold mines. There are many people around the world living in luxury off the back of landfill gas. There are, unfortunately, quite a few licking their wounds. From landfill gas, the Organics Group moved to leachate treatment in the late 90s, as well as pyrolysis and gasification. We're now focused on thermal ammonia stripping, refuse-derived fuel, biogas, and of course, landfill gas. The contents of the presentation are split into 3 sections: an overview of landfill gas technologies, a review of the key elements of success within a landfill gas project, and finally, a review of some projects with which we have had an involvement, both successes and ones of mixed performance.
In this section, I'll give an overview of the main elements of a typical landfill gas project. The intention isn't to provide a great deal of detail, but to set out the framework within which landfill gas projects are built and operate. Landfill sites come in many shapes and sizes. The main requirements, however, as far as landfill gas is concerned, is that the landfill doesn't leak. So this slide shows one slope of a project where a landfill gas system was installed. Unfortunately, it transpired that the slopes were like giant holes and let in large quantities of air, diluting the gas and then killing off the anaerobic bacteria. So the question is, what's required of a landfill site? First, it should be free of leachate, or leachate must be removed. It must be sealed with a cap to prevent the ingress of air and excessive rainwater. It should be well drained. Landfills filled with sludge are not of any use for any landfill gas extraction. There are many other requirements, though, such as good access and some degree of stabilization. But these are the main non-negotiable requirements. And here we have a manifold system showing needle control valves, individual line flow meters, and gas monitoring facilities. And the next question, what is required of a gas collection system? And one thing that's required is you need to extract landfill gas without excessive pressure loss in the pipework. You also need to facilitate, also to ensure water doesn't block the pipework, also to prevent leaks of air into the landfill gas, and lastly, not break when the landfill gas or landfill site settles. And again, there are many more detailed requirements, but these are just amongst the main ones. Now, this slide presents a quick overview of a landfill gas feed train. Landfill gas can contain many trace gases, some of which are highly corrosive. In some cases, oxygen and nitrogen can be present in elevated percentages. The feed train is designed to process the landfill gas into conditions suitable for use in specific equipment to be employed. So in this schematic, landfill gas flows firstly to the hydrogen sulfide bioscrubber. H2S is rarely present in landfill gas, but when it is, it can be in enormous concentrations. So removing protects all other downstream equipment. Carbon dioxide can also be removed, if necessary, for a particular application by a number of techniques. So here we show a water scrubber. The blower skid introduces pressure that extracts the gas from landfill site and delivers it to the point of use. A chiller will be required to remove moisture and to avoid condensate in process lines. But from there, you can go directly to the biogas point of use. Or there may be a further requirement to process the gas, for example, with a granulated activated carbon column, which can take out certain trace gases, such as halogens and mercaptans. Siloxane is another gas which can be quite damaging, so removing siloxane from the landfill is sometimes necessary. A final particulate filtration process prior to the biogas use is also advisable. Most gas engines can't. So on to the gas delivery unit. Gas enters through the inlet knockout pots designed to remove an airborne condensate and filter out coarse particulates. And in this case, then it passes to a centrifugal gas blower, which condenses the landfill gas to the required delivery pressure. We then have flame arresters located prior to the dewatering chiller, and here the gas temperature is dropped well below its dew point and then reheated into a counterflow heat exchanger. So this is the knockout pot located after the gas chilling heat exchanger to catch all of the condensate produced. From the chiller, the gas passes to an exit filtration unit where particulates are removed, and in this case down to 3 microns. Now this view shows that the other side of the same unit, see more clearly the counterflow heat exchanger inlet, which hot gases reheat outgoing cooled gas to drop the relative humidity. The dewatering chiller can also be seen more clearly. Organics uses a compact finned tube block, which has a high rate of heat transfer compacted into a relatively small space. The blue unit you see there at the end represents the refrigeration unit. Now, this is for the gas dewatering unit. This is a unit we supplied to China several years ago. In this case, we used a shell and tube heat exchanger for the dewatering of gas, as you can see here. This is a viable alternative, but it just takes up a little more space. The condensate collection pot can be seen at the end. We generally like to reduce the temperature down to 4 degrees centigrade, but less than 20 degrees centigrade, it's still a workable. The cooler the gas, the better the control of trace gases and moisture. Now for the gas blower, there are several types of blowers suitable for landfill gas, but generally we prefer centrifugal blowers unless a high pressure is required. So above 500 millibar, the blower may need to be a roots type blower, and above say 1.5 bar, we would opt for a screw compressor. Gas blowers come in many different shapes and sizes. Here we have a series of 3,000 meters cubed per hour of gas blowers, each rated at 400 millibar pressure. 450 millibar is high for a typical biogas utilization system, where 300 millibar would normally be adequate enough. Now, in this case, the higher pressure was required because of a long pipeline to the point of use. It can be variable from as small as 50 cubic meters up to 20,000 cubic meters per hour, or even more. So what are the key requirements from a gas blower? And the first thing is to facilitate flow control, also to accept a certain amount of moisture, not to corrode, to run continuously for a number of years without breaking down, and lastly, not to leak. So those are some important things to consider. On the next slide, we have hydrogen sulfide bioscrubbers. H2S isn't often encountered with landfill gas, but it can be a serious challenge when it is. So here we have examples of hydrogen sulfide bioscrubbers. They can actually be a vertical one or horizontal, but people tend to prefer vertical as it requires less installation space. The hydrogen sulfide bioscrubber prevents corrosion in downstream equipment. Hydrogen sulfide damage boilers and gas engines very quickly unless it's removed or unless great care is taken while it's being used. The bioscrubber also reduces hazards to health. Hydrogen sulfide is a very highly toxic gas. Comparatively, small amounts can kill you outright. 800 ppm, for example, is a lethal concentration for about half of humans for about 5 minutes of exposure. And concentrations over 1,000 ppm could cause immediate collapse, loss of breathing, and even inhalation of a single breath could kill you. Now, removing hydrogen sulfide from biogas reduces emissions of sulfur dioxide. The bioscrubber also reduces noxious odors. Now, a typical bioscrubber can cover, typical bioscrubber can remove about 98% of hydrogen sulfide in biogas. Basic requirements of a biogas scrubber include US to levels of 200 ppm typically. Not to be expensive to operate, it needs to be fairly cost prohibitive, and to minimize downtime. Now on the next slide, we'll cover siloxanes a little bit. There are several methods of controlling siloxanes in landfill gas. This is a process and instrument diagram for the approach adopted by organics. So gas here enters here and passes through an initial dewatering system as above. The condensate is removed in this knockout pot and then enters a supercooler where the temperature is dropped to -10 degrees centigrade. This is necessary to condense out the siloxane gases. The gas then enters a gas blower where the heat of compression raises the temperature back above freezing point of the gas with an activated carbon bed. This unit provides a final siloxane filtration prior to use. And in this case, the carbon column is followed by a particulate filter. So on the next slide, we'll get into flare stacks. There are many different types of flare stacks. And this graphic is an enclosed flare flame. This type of flare is designed to ensure very high levels of destruction of combustible gases. It started out in the form here to tackle landfill gas trace gases, such as benzene, halogens, and vinyl chloride, all of which can be detrimental to human health. Now, more recently, it's been used to control emissions of methane for greenhouse gas control. Open flares can have up to 15% methane, bypassing the flame, whereas in this case, destruction of methane can be well over 99%. Is held at a minimum temperature, typically around 1,000 degrees centigrade, for a minimum period at this temperature of 0.3 seconds. So these are the standard conditions required to be met by the UK Environment Agency. A few more flare stack options. The unit on the left-hand side with the two gentlemen in blue is what we call an open flare. The arrangement is perfectly acceptable for use as a standby flare for intermittent use. The flame burns out in the open, and there is no reliable means of measuring destruction efficiency with open flares. The unit in the middle is fitted to a plant in Turkey where the requirement was to hide the flame and to maximize methane destruction efficiency. The units on the right-hand side are located in Australia near Melbourne. They were installed close to a housing estate where there was a requirement to avoid the visibility of maximize emissions control. Now on the next slide for gas utilization, there are several viable methods of utilizing landfill gas. For power generation, it's for steam raising and is used as a vehicle fuel. Simply burning the fuel is just a waste of energy. And this particular flame was recorded during a landfill gas pumping trial at the Ipoh landfill site in Malaysia. The key opportunity for landfill gas use, however, is to generate electrical power. where it is viable. That means there must be a viable FIT or feed-in tariff as well. So in such a situation, there needs to be a reliable off-taker who will take 100% of the power produced in a 24-hour period.
Hi, I'm going to cover some of the elements of a successful landfill project. I'm going to cover management, feasibility studies and design. My colleague Brian Johnson will cover construction and operation. In terms of project management, it's intended to avoid confusions, not create them. Clear lines of responsibility are required between the parties, including owners of the landfill, the equity partners in the landfill gas energy business, normally referred to as perhaps the IPP or independent power producer, the lenders, the technology providers, and the overall system designer and integrator. We need to avoid over-optimism in terms of overstating data when it comes to attracting equity and investors and the bank's lending support. And where political objectives are senior to engineering and commercial realities, you can expect trouble. And last but not least, need to ensure adequate insurance is in place. Unforeseen events and accidents have to be covered. Clearly, the feasibility study is the start of a project, and it's extremely important to get it right. In terms of the things that needed to be covered, it's important and well, let's say essential to correctly estimate the ongoing maintenance costs in advance. The project has to have an adequate feed-in tariff, and really it needs a very robust and correctly interpreted financial model. There has to be a viable leachate management plan in place, and a good capping for the overall site is essential. It's important to look at the history of how the landfill's been maintained and planned, and correlate that with what's on the ground. And finally, a correct gas production estimate is critical. Now, talking about gas production estimates, there's quite a lot of information to consider, but you need an honest interpretation of the mathematical models, decide whether a pumping trial or no pumping trial is going to be required, avoid optimistic interpretations of results in the initial site assessment. A valid assessment of waste degradation curves and yield modelling is important. Accurate waste tonnages and composition. Pressure from investors to enhance the gas production expectations mustn't be supported. Correctly define the genset's efficiency and availability, and carefully check the landfill history for fires, etc. Look for signs of ongoing or unaddressed fires. Typically that might be elevated levels of CO2, carbon monoxide, or hydrogen, or indeed hotspots that may be obvious on the ground. Regarding landfill gas production curves, there are 5 distinct phases of waste decomposition within landfill, following the arrival and deposition. The first phase is relatively short, being the aerobic phase where free oxygen is consumed by aerobic bacteria, and the production of hydrogen commences at the same time. Once all the oxygen is removed, the waste decomposition moves into a noxic phase where the carbon dioxide is produced. This can last up to about 6 months. The third phase represents the commencement of methane production, the reduction of carbon dioxide production, and it's the commencement of the growth of the methane production producing bacteria. Phase 4 is the full methanogenic phase, where methane is produced in the maximum quantities and the gas can be recovered from the waste. In the final phase, when the methane production starts to decline, this can happen. Well, when this happens, it's extremely variable. The rule of thumb is 7 to 10 years, but it could be as little as 2 or 3. And the duration of this cycle, the duration of all these cycles can be anywhere from about 10 to 80 years or more, depending on the quantities of waste in the landfill. Now, landfill gas modelling is clearly critical to the success of the project. There's several established models for estimating the production of landfill gas, but great care has got to be taken in using such models and interpretation of such models. As you can see in this slide, we've presented the output of two different software packages, our own, Organics, and one used by the US EPA. It can be seen from the two models that they give very different impressions of the output of gas from the same site. The EPA model indicates that 1 megawatt would be achievable within a period of 10 to 15 years. In terms of the two best cases, the Organics model suggests that 1 megawatt may not be achieved. We see this time and time again, and many mistakes have been made with the interpretation of this sort of data. It's Organics' view that one should always be conservative with the gas projections. General rule of thumb is to use 30 to 50% of the realistic estimate of the gas produced in phase one of the gas project. If that's not viable, then an investor should be aware that there's increased risk. A project built on capacity which isn't there will obviously experience difficulties down the line. In terms of design is of paramount importance. Landfill gas technology is largely well defined with many suppliers. It's the integration of the systems where the problems arise. It goes without saying that equipment should be correctly specified and sized, but it remains an area of difficulty too frequently encountered. The gas engine must be suitable for landfill gas and should be well proven and have a good track record. Similarly, collection of the gas and the fuel transport system should be built for purpose. Gas wells suck into leachate, for example, will not produce landfill gas, obviously.
We would all like to think that construction wouldn't be a source of fundamental difficulty. However, some issues that can be encountered include wells not drilled to the required depth, but simply to first contact with leachate, horizontal pipework laid flat, resulting in water sealing when settlement occurs, dewatering points out of which water cannot flow, leading to the dewatering pot flooding. Another is that full-face gaskets left in a pipe, blocking all flow from that leg of the gas field, poorly found and out of sight, and lastly, incorrectly sized pipework and valves blocking collection full flow. So that's just to name a few. It's clear that construction works should be monitored and recorded. A good design can perform like a bad one if it's installed incorrectly. It's often said that a good operator can make a poor installation run well, and that a bad operator can destroy a good installation. After assessing feasibility, designing and installing a good system, it will now be critical to ensure operation is attended to with equal attention to detail. There are many aspects that come into play here. This and the next slide highlight some of those main issues encountered, which need to be attended to for operation of a landfill gas project to be successful. Fires, engine maintenance, and the like are basic. Because landfill gas requires multiple, to have in-house technicians who can work across technologies. Subcontracting out skills should be undertaken with great caution. For example, if there's a problem with a gas well, which translates into a problem with the gas engine, an engine technician may or may not understand what's going on. But a staff member who works with the gas collection system and the engine will see the connection immediately. So to this end, staff training should be recognized as fundamental and should be ongoing. Site technicians will never learn everything about a system, but the more they learn, the less downtime is experienced and the more job satisfaction they will have. Being ready for the expected and the unexpected can be planned for. So if and when this does happen, it's immediately and comprehensively addressed. One problem that's often encountered on active landfill sites is the coordination or lack thereof between the landfill and the landfilling operation. Problems can always be managed professionally through regular coordination and cooperation. Hoping for the best shouldn't be a management strategy. Leachate, unfortunately, is a problem that must be addressed in many landfill sites. Even with good basal draining, perched leachate will still be found and generally provide difficulty in extracting landfill gas. Leachate must be managed from the outset. If necessary, it may be removed using gas wells. Once removed, though, it needs to have somewhere to go. It's sometimes surprising how much leachate comes out of a site. So this may result in the need for holding lagoons and treatment facilities so the leachate can be discharged to a watercourse or wastewater treatment works. Leachate treatment is a huge subject in itself, but suffice to say, treatment since the early 90s and has most commonly found that the activated sludge process is the dominant technology used in various forms. A sequencing batch reactor is one such system that is used. This can be added as a separate equipment for removing ammonia and other trace compounds, such as heavy metals. Organics has also developed a patented thermal process, which can run on the waste heat of gas engines to remove ammonia and recover it for use or sale as a traded commodity. There are several brands of engines which have a proven track record running with landfill gas. Jenbacher and MWM Caterpillar are a couple of the main ones. Other engine suppliers such as Guascor or Shandong are also gaining traction in the market. The slide here shows Jenbacher engines being fed with landfill gas from an organic. This particular installation is in China. These parameters are a sample of what is required in terms of gas quality for an engine. Of particular importance, a few items to pay attention to when it comes to landfill gas are moisture content, gas temperature, and sulfur content. High levels of hydrogen sulfide gas, for example, can destroy an engine in no time. Siloxanes are another engine gas contaminant that can seriously damage a gas engine. It's the nature of the beast that siloxanes can appear or disappear from a specific landfill gas flow. So care is always required to see the telltale signs, which can be seen in the oil, in the piston heads, or the turbocharger.
In this part of the presentation, we'd like to bring you some real-life experiences with projects from various parts of the world. Analysis as to what went well and what went wrong is not something that we can do in such a short discussion, but we can give some of the main headlines, such as how much waste was in place, how much gas was anticipated, and how much was actually achieved. There are a great many successful projects in opposition now in many countries, but there has undoubtedly been quite a high rate of failure for reasons previously discussed by my colleagues. In this first project, this is an early image of the Puchong project in Malaysia, taken shortly after commissioning. A feasibility study was performed by the client, TSPL. It was agreed to install two 1 megawatt Jenbacher gas engines, and the site was active and had about 4 million tons of waste in place. So according to the rule of thumb, it could have produced 4 megawatts. The project was a technical success with plenty of gas. There was a requirement to remove leachate from the gas wells, and this was done very easily. The project won first prize in the Renewable Energy Project Competition on-grid category at the 2005 ASEAN Energy Ministers Meeting in Siem Reap, Cambodia. One difficulty that did arrive was that the feed-in tariff was quite low at the outset, feasible but low. During implementation of the project, the euro rose in value, and the budget set in Malaysian ringgits was stretched to the point that the operating budget was used to pay for capital equipment. And this resulted in some difficulties during operation, but I'm happy to say that these were resolved, and the project is still in operation 15 years later. The next example was a project built in Turkey in the year 2000. The waste in place was in the order of 6 million tons. A pumping trial was performed by others, and the results indicated that 6 megawatts could be generated. So it was decided to install 4 to be on the safe side. These were 1 megawatt Jenbacher gas engines, and space was left for an additional 2 engines as long as there was adequate gas. In practice, after everything was installed and operational, it was found that the maximum capacity that could be generated was 2.5 megawatts. The shortfall was probably due to the fact that the pumping trial didn't cover the full area of the landfill, and the missing sectors were probably not as productive in gas generation as the ones tested. Nevertheless, as the project was owned by the city of Istanbul, where a certain Recep Tayyip Erdogan was the mayor, the project was declared a success and continued in operation. The next project was installed on a site where a pumping trial carried out by others had indicated that the generation potential was 35 megawatts. There were approximately 6 million tons of waste in place. Following organics involvement, this was revised down to 4 megawatts, a maximum quantity. In theory, the site might have been able to produce 8 megawatts if the waste had been landfilled correctly. But in fact, it had been open dump for much of its life. In the end, pressure from the investors led to 8 megawatts being installed, and at first operation, the site produced only 2.5 megawatts. The great saving of this project was that the site was active, and the waste coming in was coming in at the rate of about 4,000 tons per day. It eventually reached full capacity and is still in operation. Our next project, case study, is of a landfill gas utilization project installed in the Garraf landfill site near Barcelona in Spain, a landfill with a total of around 40 million tons of waste in place. After a public tender, 12 1-megawatt Jenbacher gas engines were installed and commissioned in 2003. The site was closed to waste input in 2006, and the site was restored to a high quality, a process that involved the import of large quantities of earth. This caused the leachate in the site to rise up in the gas extraction wells and reduce the gas collection efficiency of the gas extraction system. But during the commercial lifetime of the project, the maximum number of engines achieved then was 7 megawatts. However, due to the acceptable feed-in tariff, the project was successfully operated until the end of the contract, after which time the plant was transferred to the city council. As the site was closed in 2006, the gas generation curve commenced to decay almost immediately, and the project is now producing 2 megawatts, although new extraction wells are now being installed to capture any additional gas that may be being generated. So, what of the future of the industry? Landfill gas technology is mature, and it's been shown that with judicious management and proactive legislative support, projects can be commercially successful, although it's highly important to understand the risks involved. There's little doubt that landfill gas management will remain an important consideration in those places that still accept organic waste to landfill, such as in Malaysia and Indonesia, but will decline in importance in places where organic material is not permitted to be landfilled, such as in Europe. Organic material is more frequently being separated, and technologies that use anaerobic digestion and other mechanisms will eventually take over producing biogas. But there remains no doubt that for the foreseeable future, landfill gas management will be a requirement to ensure that a highly destructive greenhouse gas is not released in an uncontrolled manner to the atmosphere. That brings us to the end of our presentation, and we will open the floor to questions. If you'd like to ask a question, you can do it either by raising your hand in the control panel, and you'll be able to ask your question directly. Alternatively, you can write your question in the box provided, and our IT expert will pick it up and direct it to the most appropriate person for answering. Thanks for your attention.
Hello, would anybody have any questions? Any questions from the floor?
Not yet, Keith. Looks like they're taking their time.
All right. I have a question here. What exactly goes into a landfill gas feasibility study? Perhaps Rob, you want to answer that one?
Yeah, okay. So a feasibility study can comprise a lot of things. I once heard Dick Pacey, who was the grandfather of landfill gas, he said, if you do everything that you can possibly do to assess a landfill site, at the end of the assessment, you'll be left with an uncertainty of 30%. So, so it's actually more of a black art than a science. But normally you'd start with a study of the waste infilling on the landfill site. You need to know the organic content of the waste and how much waste has gone in over the years, so you can start modeling likely outcomes. But you have to know, like the site that Chris mentioned, the third case study, the first pumping trial that was carried out indicated enough methane to generate 35 megawatts from 6 million tons. So, and these are serious people who've spent a serious amount of time working out how much energy, how much electricity they could generate from the gas. Anybody who's been involved in landfill gas for any amount of time would know the rule of thumb is 1 million tons is 1 megawatt for 10 years. That's where you start. Then you have to take into account things like how the waste has been deposited, and if it's an open dump, then it may well be that 1 million tons gives you nothing. So it needs eyes wide open. I think really an essential part of a landfill gas feasibility study is the pumping trial. And the pumping trial has to cover all of the waste that's going to be extracted. So you may have to put in 4, 5, 6, 7, 8 wells to ensure that you cover all of the waste where you're hoping to get gas. Because some of the waste you may find, like in the case of Kenmare gas, has no gas at all. And if you've added the gas from that section into the total, then you're going to come up short. So that's the answer to that question.
All right, thanks for that one. Someone's just asked, could we explain a little bit more detail regarding what to do with digested material after it's obviously degassed?
So
With what material?
With the landfill, with the digested material. So in other words, degassed waste. So it's broken down in the landfill. Can you mix it with the new waste, or will it affect performance?
If new waste goes on inert waste, it's not a good. You try and keep the two systems separate.
Do you mix it? Obviously, landfills laid down in layers, in cells.
Yes. Yes.
So it's not necessarily something that you're going to necessarily commingle, and it would probably be worth the effort to actually mix it, unless there was some sort of like well, an AD facility. I mean, effectively a cell, which is an AD cell or something. But I wouldn't have thought there's any benefit to doing that.
No, I mean, the only time I've heard about disturbing an old landfill site is when you mine it for recyclables that might have been missed in the 80s and 90s when recycling was less popular. There were various activities like that in some of the European countries. Holland, I know, had quite an active mining industry. But apart from that, no, once the waste is inert, it should be allowed to be inert. And after, I think, 50 years, you can build on it. But apart from that, fresh waste should go into a new landfill and correctly managed, and then the gas extracted from that.
Yeah. Okay. All right. Hopefully that answers the question. I mean, if there are any questions subsequently to this, or nothing's clear, please do send us an email or respond to the GoToMeeting webinar reply that you'll get at the end of the session, and we'll pick it up from there. Okay. One other question is, would you always recommend doing a pumping trial? Is a pumping trial essential to a good feasibility study? And I guess the question really is, are there any occasions where you wouldn't do one?
I think the pumping trial wouldn't be necessary on a site like the third case study that Chris mentioned, where they had 40 million tons of waste, and the project was viable with 6 megawatts. So 40 million tons and 6 megawatts means that the risk is actually very low. But then you'd have to have a pretty good understanding of the way the site was filled, what's actually in the site, how it's been capped. Was it open dumped? If it was open dumped at all, then the chances are that during that period it was a huge compost heap, and there was no methane produced at all, and the waste stabilized during that period. So, but I would be very wary about not doing a pumping trial for a landfill gas project. Not vital, but you need to be careful.
Okay. How would you design a representative pumping trial, and what would it cost?
It depends on the site in question, but personally, I think you need at least 6 wells, preferably 10. And gas wells cost as much as they cost, maybe $3,000, $4,000, $5,000 a well. So that's a big lump of money there. So really, depending on the size of the site, the amount of pumping you want to do, you're talking about $100,000 up to do it properly.
Okay.
I see a question there, Keith, about 4 wells out of 10 not producing gas. Some possible causes of what that could be. That's a very long discussion, but on a new landfill, if it's just been installed, I think if they were producing gas and now they're not, the first thing I would check is that you're not over sucking on the well and causing air to be drawn into the site around that well. If you're over anxious with the extraction and you're trying to get as much gas out of the ground, there is a danger that you can then pull atmospheric air from the surface into the landfill site, and that's when you kill the methanoic bacteria and you stop producing landfill gas. So I notice you're asking for a colleague who's working on there. I would suggest the first thing to do is nothing, and just see if those gas wells recover with no suction being applied to them. If the gas does recover, then very, very gentle suction, just 1 or 2 millibar, and try and find the extraction rate of the well rather than trying to overwork it. Plenty of other reasons, cracks in landfill site covers, oxygen ingress, blockages, water flooding, condensate flooding in the well. But assuming the obvious is out of the way, then I would expect or some route for oxygen to get into the site.
Okay, thanks for that. And another one would be, what do we look out for with a reliable gas engine? What makes for a good, reliable gas engine?
Can't beat track record.
Apart from young.
I think
Yes.
experience is everything.
Yeah, experience is everything.
The number of engines that somebody sells is always a good indicator.
Yeah.
Mm.
You can get some
Pitfalls
bargains.
at O&M.
Yes, I mean you can get them cheaply, but you have to be aware that if you buy them cheaply, you're going to have to be putting in some money to bring them up to standard. There was a company in Australia that was doing very well importing some Chinese engines, spending all the money that was required to bring them up to Australian standards. And they were still cheaper than the local competition, but to get a product that is actually going to be reliable, you can't beat track record.
Mm.
Yeah, I mean, another important point is that I once saw some Dorman diesel gas engines, and they, I mean, I hope nobody from Dorman Diesels is listening, but they were absolutely terrible. They were a diesel engine converted to run on gas, and with all of the problems that resulted. So they kept breaking down the turbochargers, the piston heads, the cylinder heads, everything kept breaking. But they had this fantastic operator, and he was doing predictive maintenance. So he had all the spare parts on a shelf in the workshop, and he could tell by the noise of the engine when something was going to go wrong, and he'd fix it before it broke. So he was hands-on, and he got a very high availability. So I think the lesson I learned from that was that a good operator can run a bad engine well. A bad operator can destroy a good engine in no time at all.
Yes, I think it's very important to emphasize that point. On the Garage Landfill site, we rebuilt a Wascore engine, and we got a very high availability from that Wascore engine that was something like 10 years old, all due to the experience of the operator. I think it shows and highlights the importance of the value of the operators and the training that needs to go into ensure the availability.
And what sort of availability, what's the optimal availability that you could expect out of an engine realistically, well maintained by third parties?
We used to, the availability that you use in your financial models, you always try to be on the pessimistic side, is around about 85%. Sometimes we got availability of up to 96%. And again, it comes right down to the efficiency and the efficacy of the operations team.
Yeah.
Right.
You had some very good bonus structures in place that meant that anything over 90% efficiency, the operators shared in some of the profits from that.
Exactly. There has to be incentivization all the way along the chain.
Yeah.
Yeah. Okay. In terms of monitoring, what sort of equipment do we use on for gas monitoring?
Well, we're typically monitoring the gas, particularly if we're delivering it to an engine. So that's the methane and the carbon dioxide and the oxygen. We have to often monitor the emissions from flares, and that is for things like NOx, nitrous oxide, sulfur, and carbon monoxide and carbon dioxide, and just to confirm that all of the hydrocarbons and volatile organic compounds have been destroyed correctly. We've monitored for moisture, temperature, pressure, many other things on the gas stream itself. And typically it ties into another question you can see down here is if there's a leak or fault on the system. If the system is under suction, which it typically is with a landfill site, then oxygen is drawn in, and you can pick that up with the sort of detection techniques that we use for analysing the gas. Looking for elevated oxygen levels is a very good way of tracking a fault through a landfill system.
Right. Yeah. Yep. Yep. Okay. And in terms of fires, do we have any experience of fires, deep-seated or shallow? And how would we recommend we deal with those? I mean, clearly that's an aspect of design as well in terms of looking for either fires, as we said in the presentation.
It's an aspect, it's a very fundamental aspect of the landfill site design. If the operator is not careful in the daily capping, fires can either break out at the surface, which can then go back into the landfill site. And we've seen on several occasions where there have been open fires on the top of a landfill site with the pressure of the gas coming out of the landfill site, newly installed waste. The other type of fires, which are deep-seated fires, and which leads to a process of pyrolysis within the landfill site, a sort of burning front. And again, those are very difficult to detect, but something that should always be looked out for. Yeah.
So just jumping into, so one of the questions that I've seen coming in on my feed here is, hi, is landfill gas tapping feasible for small landfill, say, of less than 500 tonnes per day? So as was mentioned previously, but it depends on how long you're do your 500 tonnes a day for. It's been mentioned already, the million tonnes for a megawatt. So as long as your landfill is correctly lined, correctly filled and correctly capped, and the management is correct during that, then you can extract, yes, it is worth doing. It depends how long you're doing 500 tonnes a day for. That's a healthy feed. So yes, I would think there's certainly something to look at there.
Yeah, another rule of thumb for an active landfill site is 100,000 tonnes a year is equal to 1 megawatt. So if you're getting 500 tonnes a day, you're getting 150,000 a year. You should get, as Mark said, as long as there's enough waste in the site, you could be looking at 1 to 1.5 megawatts. But that's subject to all sorts of qualifiers.
Yes, don't start building on the back of that. There's feasibility studies to be done yet.
Yeah.
So another one that I've just spotted on my one, does the flaring system able to fully control, destroy the emissions of hazardous gases produced? Yes, broadly speaking, so that we design at a temperature suitable to the country. So if we're operating in Europe, that's 1,000 degrees mostly, and through Asia it's 1,000 degrees. The Americans like 850 degrees centigrade. But we also ensure successful residence time at these temperatures to make sure full destruction. Probably the only exception that we can't destroy are things that come in on the inlet. So that if there is sulfur on the inlet, when that is combusted, oxidized, it will form oxides of sulfur, SOx, which is why we have H2S removal on the inlet of a lot of these flares. So as long as the gas is destructible into a safe product, then yes, it will be. The residence time is to do that. But if you were to send us a more specific request on what you need destroyed, then we could have a look at it. But yeah, there are very strict emission standards that we have to comply to, and we do.
Sorry, I'm just my questions have disappeared there. Regarding the did you answer the first one there, Mark? Is that on the list?
About the 500 tonnes a day, yes, we looked at that one.
Yeah.
And then we'd already touched on the idea that the wells were not producing. I think we've covered that one.
in terms of the 500 tonnes a day?
Yes, well, Rob and I've just talked to that one. 500 tonnes a day. One rule of thumb that would give you your 100,000 tonnes per year for 1 megawatt, so potentially 1.5 megawatts. But many, many different things to be looked at first. Among them, is it covered at night? Is it dumped correctly? Is it managed in a correct way? Is the leachate managed correctly? So there's very, very long list to be checked off, but on the information we have, but we need to know an awful lot more.
I think this is an important point in terms of the pumping trial as well. I mean, from my point of view, a pumping trial is really just a snapshot in time. A lot of people view a pumping trial as something that is a finite exercise. So you install your wells, you put your test rig on, and you do a 4-week pumping trial, and that's it. And you get your financial model out of that. For me, a pumping trial is the installation of a full gas extraction system with a control flare stack that is there semi-permanently until there is a knowledge that you've either got a utilization project or it's just a gas control project. I think I would be less inclined to do a pumping trial on a site that's got a lot of waste in it, like 40 million tons. I'd be interested in knowing where the leachate is, what else is wrong with the site. But if I had a site that was 500 tons a day, a pumping trial is absolutely imperative, and a long-lasting pumping trial is imperative if you're looking at doing a commercial project.
Yeah. Mark, I don't believe we answered this question there regarding the some wells actually. The landfill is in commissioning in year one.
Yeah, I just mentioned that a little bit about that in the back end of another question you asked earlier, Keith, about if that was my site and 4 wells were producing gas and are now not. I would think it was probably due to over extraction, and that the best advice would be to rest them for a bit. So no extraction, and then when they do come back to life.
And
it depends how big the project is. I mean, what are we looking at in terms of the size of the project? If it's a 200 kilowatt project, 4 wells probably isn't enough.
The question is about 4 out of 10. 10 installed, 4 not working. So
even 10 wells, I would. I mean, if we look at a worst case scenario, we can look at, say, or a good case scenario, say 20 cubic meters per well if we can produce it.
Yeah.
And how does that evolve with time? Because the other thing,
where are you in terms of the gas curve, the production curve?
Yeah, where are you with the gas curve? How does it involve with time? And that information you get with a long-term pumping trial.
Yeah.
I mean, if
there are that many wells not producing gas, then I think great care needs to be taken, because that's a sign that you're looking at aerobic decomposition.
Yeah.
And if the site goes aerobic, then the temperature goes up, and all of the organic waste goes to carbon dioxide, and there's no methane comes out at all.
Okay, so perhaps in culmination on that one, perhaps if you were to get some more information for us, we could take a closer look at that and give you a more calculated response.
Yep, absolutely.
All right. Are there any more questions? Okay.
There's one here in the event of leakage or a fault in the system, how would landfill gas be managed?
Yes, sort of mentioned towards that one. I assumed it was a question more about how would you know about the faults? Because obviously, if the system fails, if the landfill gas management system fails, you can't manage the landfill gas. But you can put in place ways of detecting failures before they become problematic. So monitoring the pressures, suction pressures to look for blockages, monitoring the oxygen levels to look for oxygen ingress leaks. And I'm a big fan of visible pipes and people looking at things. And because landfill sites are organic systems themselves, they're animals, they move. So the more visibility you can have on your pipework, the better, so you can keep an eye on things like cracks around well heads and movement on well heads and movement on pipes. I think the only bit of wisdom that I remember receiving to do with this was, or the most said, if you manage the water, the gas will manage itself. So condensate and just managing the liquid flows, the gas will find a way as long as you get the water out of the way. So perhaps that would be the most critical part to look at in terms of potential failures of a management system.
I think, building on what you said and something that Rob said earlier, preventive maintenance is essential in a landfill gas extraction scheme. And this right down to operator involvement and training, and the systems that you have in place for ensuring that you're doing preventive maintenance on every aspect. Exactly what Mark has said about right from the well right through to the electrical connection. So it's very important, the preventative maintenance aspect.
Yeah.
I think the follow-on question for that, I'm not sure whether we've answered this one already, but disregarding does the flaring system, does it actually destroy the emissions of hazardous gas produced? So if it was flaring alone, I mean, clearly a lot of projects are purely flaring to control landfill sites. It's not necessarily producing power. I guess it depends on how well compacted the landfill is, etc. Clearly flaring
that talks about that touches on the question that's just come in. Is really, is there any the safety measures that have to be taken?
Oh, for sure. Yes. Yeah. In terms
I think
of
it's very important to realise that a landfill site is actually a dangerous place, and it needs to be carefully managed. There are all sorts of things that can go wrong. If it's not got proper sanitation, then I would be very wary. But gas flaring, as long as you can do the not only the pumping trial, but the assessment. You should do a desk assessment of every parameter of the landfill site, all the information that there is. There are test holes to drill to know exactly the nature of the landfill site. But gas flaring should be a problem.
I think this is also touching on a problem that we're facing more and more in the UK now, that the methane level is dwindling to lower than flareable levels, and you end up with a gas production of a low quality methane, high CO2 and often high nitrogen mix, which is not really safe. So below about 18-19% methane, it's very difficult for it to sustain a burn and be flared correctly. But then you've got 20-30 years of a landfill site producing somewhere between 18 and 0% methane, and during that time that gas is still dangerous and explosive. There are some low calorific burners available that can take 7 or 8% and burn it with the use of a regenerative thermal oxidizer, and often with a pilot gas as well. So there are things you can do. They're often not cheap, and usually close monitoring of boundaries and make sure that you've got no gas escape into your neighbours, and then some atmospheric monitoring is the best you can do. But again, as with a lot of it's each one has its own unique problems and solutions. So if you were to give us more information, we could have a closer look at it for you.
At what point would you? I mean, clearly you can use passive wells
Yes.
as a cheaper option. At what point does the gas warrant going for, like a flare as opposed to passive vents?
This is driven often by BAT, best available technology, so that if it is impractical to try to run a low calorific burner that can take methane down to 8 or 9%, then, and it is more practical to have passive venting, then you can do a study to ensure that that passive venting is better for the environment than nothing at all. So there's often different answers, but I think
So clearly in the moment, yeah.
I think it's also a question of directing where the gas goes to. I mean, if the gas is going to be collecting in a basement, for example, then you want to get it out. So passive flaring could be the solution to that, to actually make sure that it goes to a point that is safely, where it can be safely disposed of.
Yeah. Okay, the follow-on question from Farah. Is it okay to do flaring without knowing the concentration of methane? Well, I guess you need to know the concentration before you can size the flare.
Yes, that is true, but you don't need to know once you're there. You don't need to know the concentration to burn it. If it'll self-ignite, then it's going to be around 20% plus. If it doesn't, and all the other conditions, spark, oxygen, are there, then it's probably less than 20%, and you've got to do something else. If you can get it lit, it'll maintain a flame down to 17 or 18%. But it's actually very difficult to light at less than about 25%. So you can usually feel the gas concentration it might be with those little indicators. But yeah, you don't need to know it to flare. But if it's unpredictable, then the ignition of it might be difficult.
Okay. All right. Thanks. Any other questions? Okay. Well, it looks like we don't have any more questions, but thanks for all those.
Wrap up now, Keith.
Sorry.
You could wrap up now. So these are the contact details for the people who are have taken part in this presentation. If you want to contact anybody, please go ahead. We'll welcome communication. And you can always check our website. This is one of our main websites. But if you go to organicsgroup.com, you see all of our different country websites as well. Do you have anything to say?
What about the handouts? There are some handouts here, right?
Yeah, there are 5 handouts. One is a technical paper on gas and leachate extraction, combined gas and leachate extraction systems, written by a very famous author. So that's it. Yeah.
Those handouts, Rob, are they available afterwards or only during this session?
I think if you get them, you
Yeah,
can
if you don't have a chance to download
get them from.
We'll send them back.
Yeah, if you want anything, you just let us know. Okay. Thank you very much, ladies and gentlemen.
Thank you.
Hope you have a nice day and enjoy your lot. Bye-bye.
Thank you. Bye. Bye. Bye.
Bye. Bye.